Welcome back. Last time we discussed the UCB algorithm, which is the main frequentist algorithm for the multi-arm bandit problem. This time we are going to analyze its performance. So we are going to derive bounds on the regret of the UCB algorithm. Before we start, you should make sure that you recall the algorithm, or better still, have it written down somewhere so you can refer to it whenever you need it. So just to recall very quickly, the set of assumptions we have. We have K Bernoulli arms. The UCB algorithm works as follows. It plays each arm once to start with. In subsequent time steps, it computes an index for each arm, which consists of the sample mean reward obtained on that arm up to that time, and an additional term, which you can think of as an optimistic correction term, which gives an advantage to arms that have not been played too often until that time. So it's an extra term to say maybe the true mean is a little bit bigger than the sample mean I observed. So there's at least a 10% or 50% chance that the true mean is bigger than this number, and it's this upper threshold of my confidence interval which I'm going to use as my estimate of the reward from this arm. So that's the idea behind the UCB algorithm, and today we are going to look at how well it performs. I'll start by stating our main result right away, and we are going to spend the rest of the lecture proving this result. So just to remind you, we have a bandit with k independent arms. The rewards from the different arms are IID sequences of Bernoulli random variables. Mu I is the mean reward on arm I, so it's the probability of getting reward 1, and then you get reward 0 with probability 1 minus mu I. Okay. And we assume that the arms are ordered so that in decreasing order of reward, and the best arm is unique. So the reward mu1 is strictly bigger than mu2, which is bigger or equal to mu3 all the way to mu k. Let's also denote by delta I the amount by which mu1 exceeds mu I. Okay, so this is the extra reward on arm 1 compared to arm I, extra mean reward, that's delta I. And now a statement about the regret is the following. So if we use the UCB algorithm with parameter alpha, and we suppose now the algorithm is defined for all alpha positive, but we are going to assume that in fact alpha is bigger than 1. And if that is true, then the regret incurred in the first t rounds is bounded above by this expression. Let me talk you through this expression. So we have a sum over all the suboptimal arms, 2 through k. The contribution from each arm I, each suboptimal arm I, consists of 2 terms. The first term is a constant that depends on the parameter alpha of the algorithm, and delta I, how much worse this arm is than the optimal. The second term also depends on alpha and delta I, but it's also growing with t. Okay, so there's a constant term and there's a term growing with t. And it grows pretty slowly with t. It's sublinear and significantly sublinear. It grows much, much, much slower than linearly in t. Okay. And so the regret is determined by both these contributions coming from all the arms. Okay, so the rest of the lecture will be devoted to proving this theorem. And the proof, we'll break up the proof into a number of lemmas, but first we discuss how should we choose alpha. So if you look at these two terms, the second term is increasing in alpha. A bigger value of alpha means that the regret grows more quickly with t. So this suggests to choose alpha small, but we can't make it too small because the first term is decreasing in alpha, and further it blows up as alpha gets close to 1. So as you decrease alpha towards 1, this term becomes infinite. So alpha needs to be bigger than 1, and there needs to be a bit of a margin from 1, or else this term is huge. So let's discuss this in a bit more detail. So a few remarks. So as I already mentioned, the regret grows with t, but it grows very slowly and only logarithmically in t. So compared to the naive heuristic we looked at, where the regret grows linearly in t, the UCB algorithm is extremely good. That's the first observation. And then we want to think about how to choose alpha. And we saw already that if we take it too big, then that's a prefactor on log t, so it grows quickly, and we don't want that. And secondly, if we take it too small, the constant term blows up, and this is the term that's dominant for small values of t. And in practice, we do care what happens at small to moderate values of t. We are not looking necessarily in the very long run, so we shouldn't take it too small either. Okay, and a very common choice is alpha equals 2. And that's reasonable for most practical purposes. Okay, so that's as much as I wanted to say about the choice of alpha. And now we'll turn to the proof of the theorem. As I mentioned, we are going to break it up into a number of lemmas, and the first one deals with when a suboptimal arm is played. So recalling the UCB algorithm again, in the first case steps, we play each arm once, each of the k arms once. And so we are looking at times s, which are bigger than k, and whether and under what conditions we play some suboptimal arm j in that time step. So recall the notation. S plus 1 is the index of the arm played at time s plus 1. So we are asking, suppose that, so what needs to happen to make us want to play a suboptimal arm j at time s plus 1 after the exploration phase consisting of playing each arm once? And the claim is that one of the following three things must happen if we are to choose to play arm j. And these are quite intuitive. So why might we play arm j? It might happen that the sample mean reward we obtained on the first arm in the first s time steps is much smaller than its true value. So we might end up thinking that arm 1 is a lot worse than it actually is. Okay, so the true mean is mu1, mean reward is mu1. And if the sample mean deviates from the true mean by at least this much, so it's a lot smaller than it should be, then we might think arm 1 is not very good. That's one reason. The second reason is that the sample mean reward on arm j turns out to be significantly bigger than its true value. We just got lucky by chance on arm j, and instead of observing the true mean mu j, the sample mean reward in the first s time steps is bigger by this amount than the true mean. Okay. So these are two natural reasons why we might prefer to play arm J to arm 1. And the third reason comes from the optimistic correction term. Maybe arm J was played very few times until time S. So the number of times Nj of S that arm J was played is smaller than this amount. So it was played too few times, so you are adding an optimistic correction, which, if you recall, grows like square root 1 over Nj. So if Nj is small, square root 1 over Nj is big. You've added a big optimistic correction to the index, and so you want to play arm J. Okay. So the lemma says that one of these three things should happen in order for arm J to be chosen at time step S plus 1. So let's prove this lemma first. And the proof is going to proceed by contradiction. So by way of contradiction, we suppose that none of the three inequalities in the lemma holds. Then what can we say? Let's go to the first lemma. If this inequality doesn't hold, the sample mean on the first term is bigger than mu1 minus this, or if we move this term over to the other side, mu hat 1 plus this correction factor is bigger than mu1. Okay, so that's what the first inequality says. Mu hat 1 plus the correction factor is bigger than mu1, because by assumption, the first inequality is violated, and the lemma is violated. Okay, now this equality here is just the definition of delta J. Delta J is mu1 minus mu J, so I've written mu1 as mu J plus delta J. And this inequality here comes from the third inequality in the lemma. So suppose so what does the third inequality say? It says that Nj is small. And so if that is violated, let's go back up. If the third inequality is violated, that says Nj is bigger or equal to this. So if we move these things around, that says delta J squared is bigger or equal to 2 alpha log S over Njs. Okay. So delta J is bigger or equal to this. So mu J plus delta J is bigger or equal to mu J plus this. So this comes from the third inequality in the statement of the lemma being violated. Okay. And now the second inequality is also violated. What did the second inequality say? It said that the sample mean on arm J exceeds its true mean by a certain amount. So if that is violated, that says that the sample mean on arm J is not bigger. So the sample mean on arm J okay, so let's go up to the inequality here. So the second inequality says that the sample mean on arm J exceeds its true mean by this amount. So if it's violated, it says that the true mean exceeds the sample mean minus this. That's what rearranging this gets. The true mean is smaller than the sample mean minus this. So the true mean, the sample mean is smaller. The true mean is bigger than the sample mean minus this. So that's what violating the second inequality says. Plus this, we copy this over. And then this last equality is just algebra. Okay, so if all three inequalities in the lemma are violated, then what we end up with is that the sample mean on the first term plus this term is bigger or equal to the sum. In fact, somewhere it should be a strict inequality. Yeah, it's strictly bigger than the sample mean on the J term plus the corresponding correction term here. But what are these correction terms? These are exactly the things coming from the UCB alpha algorithm. So this whole thing here is the UCB alpha index of the first term. This is the UCB alpha index of the j term. And so what we have said is that if none of the inequalities in the statement of the lemma holds, then the index on the first term is strictly bigger than the index on the j term. And what does the UCB alpha algorithm tell us? It tells us to play the arm with the biggest index. And so if the index on arm 1 is bigger than the index on arm j, clearly arm j cannot be played at time step s plus 1. Okay. I'm not saying arm 1 is played. Maybe there's some other arm with an even bigger index, but definitely arm j is not played. But this contradicted the assertion that at time step s plus 1, arm j was played. Okay, so that was in the lemma statement. So arm j is played in time step s plus 1. So by contradiction, we've shown that if none of these things are true, then arm j cannot be played at time step s plus 1. Okay, or in other words, if arm j is played at time step s plus 1, at least one of these three things must be true, and maybe more are true. So that's the proof of lemma 1. Okay, so we found conditions under which a suboptimal arm j happens to be played at some time step. The next thing we want to do is count the number of times the suboptimal arm is played up to some time t. And so we want a lemma about counting. And this lemma has nothing to do with probability. It's just a statement about sequences. So we are going to consider a sequence, it, so t takes values in natural numbers. And this sequence can take values only 0 or 1. So we have a sequence of, if you like, coin toss. Okay, forget randomness. So we just have a sequence of numbers. It might of bits. So it might go 0, 0, 0, 1, 0, 1, 1, 0, something. So we have some sequence. And nt is just adding up the first t terms of the sequence. It's counting the number of ones in the first t terms. Okay. And the claim is the following, that if you give me some natural numbers t and u, maybe t is 20 and u is 3, then the following is true. The number of ones in the sequence in the first 20 indices or time steps is bounded above by u plus, I'll only count from time u plus 1 up to t. I'll count is. Nt consists of counting is for all time steps, but now I'm only counting from time u plus 1 onwards. And I'll count is only if this indicator is satisfied, only if by time s minus 1, the count has already reached u. So maybe for your sequence, I gave the example of t is 20 and u is 3. So maybe it was only at time 7 that the count reached u. So I'm saying that n20 is smaller than 3 plus I'm going to count is starting from time step 8 because it was only at time step 7 that we reached u. Okay, so this is just some expression, and I claim that this inequality always holds. This is quite easy. The proof, but maybe the notation looks heavy, so it might be worth just working through an example. Write down an arbitrary 0, 1 valued sequence of length 10 or 20, something reasonable. Pick a value of t, pick a value of u, do the calculations nt for t equals 1 through 20, and calculate the right-hand side also for t equals 1 through 20 and see if the inequality holds at each time step. Okay, so working through that example should hopefully convince you what's going on here. Okay, and here's the formal proof. So let's fix some natural numbers, t and u. And now there are only two possibilities. So there's no randomness here, right? So we are given the sequence it, which is deterministic. We can calculate the sequence nt, which is deterministic. And either n at this particular value of t is smaller or equal to u, or it's bigger than u. If it's bigger than u, then there was the smallest s between 1 and t for which it's bigger than u. Might be t itself, might be something smaller. So maybe u was 3 and t is 20 and n20 is 7, which is bigger than 3. Then there must be some smallest time at which you exceeded 3. Okay, so let's denote the first time at which we exceeded u by s star. Now what can happen? Notice that n is counting the number of ones in a 0, 1 sequence. So it's non-decreasing and it increases by at most 1 at each time step. So if n s star is the smallest value for which it's bigger than u at time s star minus 1, it must have been exactly equal to u. Yeah, because if it was bigger than u, it's already exceeded u by time s star minus 1. Could it be smaller than u? No, because then it would have to jump by 2 or more within a time step, and it can jump by at most 1 in a time step. So ns star minus 1 is u, ns star is u plus 1, and also s star is necessarily at least u plus 1 because n starts at 0 and goes up by at most 1 at a time step. Okay. Okay, so what is nt? It's the sum s equals 1 to t of is. So let's break it up into the sum up to s star minus 1 and the sum from s star to t. By definition, the sum of the first s star minus 1 terms is n of s star minus 1. Okay, and on the remaining terms, I can throw in this extra indicator because already at time s star, n of s star minus 1 was u. I've noted that here. And because n is non-decreasing for all future times, it's also going to be bigger or equal to u. So this indicator here will always be 1 from time s star onwards. So I can always throw it in. And as we saw, s star was at least u plus 1. So if I start summing this from u plus 1 rather than from s star, I might get something bigger, but because I may have a few extra terms here, but I definitely won't get something smaller. So this inequality holds for this term, and for n of s star minus 1, it was u. I've just copied that. Okay, so this inequality holds, and this is what we were asked to prove. This is the statement of the lemma. Okay, so this inequality was the statement of the lemma, and we've proved that. Okay, so let's go back now to lemma 1. It said one of 3 things should happen if a suboptimal arm is to be played. either the sample mean on the first term is unusually small or the sample mean on the j term is unusually big, or the number of times arm j has been played is small. So let's look at the terms, two terms where the sample mean is unusually big or small. So what can we say about those events? And the last lemma we need says that those probabilities are small. So the probability that the sample mean on the j term exceeds its true mean by this much is bounded above by at least e to the minus alpha log s. Okay, and what is this quantity? E to the log s is s. So e to the minus log s is s to the minus 1. And this is just raising that to the power alpha, right? So I could have rewritten e to the minus alpha log s as e to the minus log s whole thing to the alpha. And that is s to the minus 1 whole thing to the alpha, s to the minus alpha. Okay, and similarly, the probability that the sample mean on the first term is much smaller than its true value is also bounded above by this. So that's the statement of the lemma. Let's pause a moment to make sure that, that you completely understand the statement. So do you understand the notation? What is mu hat? What is nj? Nj is s is the number of times arm j has been played up to time s. And this is the sample mean reward from that arm in the first njs place. And we are asking for the probability that it's bigger than the true mean by this quantity, which comes from the correction term in the UCB algorithm. That's why we are interested in this event. And similarly here. Okay, so where do these inequalities come from? So how do we prove this lemma? This proof is again very easy. This is just Hoeffding's inequality. Recall that the rewards on the arm take values either 0 or 1. So they take values in the closed interval 0, 1. And Hoeffding's inequality is an inequality for sums or means of random variables, IID random variables, taking values in this closed interval. So we can directly apply Hoeffding's inequality to sums or means of the xj's, and that gives you this. I'll leave you to work that out for yourself. And similarly for arm 1. Okay, good. So what have these three lemmas given us? The first lemma told us that a suboptimal arm would only be played if one of three conditions were satisfied. And the third lemma tells us that two of those conditions, the probability of two of those conditions is bounded like this. And okay, lemma 2 is a counting lemma. So we are going to put these three lemmas together to prove the main theorem. Okay, so let's start on the proof. So let's fix some time horizon t, and we are going to define u in this way as 2 alpha log t over delta j squared. And these symbols around it say we take the smallest integer bigger than this. So if you calculate this and it turns out to be 7.3, u is going to be 8. Okay. Now u depends on t and on j. I don't want to, so I should really write u of tj here, but I don't want to make the notation heavy. So I haven't made the dependence on t and j explicit, but I'll remind you of it wherever we need it. Okay, it's not just a constant, it's something that depends on t and j. Okay, so lemma 1 is an upper bound on the regret. And the regret is going to depend on how many times we play suboptimal arms. Every time we play an arm J, which is suboptimal, we incur a regret of mu1 minus mu j. So to calculate the total regret, I need to bound the number of times I play each arm, each suboptimal arm. And our counting lemma told us that for any choice of u, we can bound nj by u plus this sum here. Okay, so we are going to use this u. And then we have the sum, which is the indicator that nj has exceeded u by time s minus 1 or equaled u by time s minus 1. And in time step s, we choose to play arm j. Okay. The notation I has changed a little bit. In the proof of the lemma, I was a 0, 1 valued random variable. And now I is the index of the arm to be played. And this 1 here plays the role of the I in the lemma. Okay, so just a warning about the slight change of notation. This 1 is the I in the statement of lemma 2. And it depends in a complicated way on the history, but that's fine. This lemma was for arbitrary sequences. Okay, so we have this inequality, and now what we are going to do, and now in this inequality, everything here, these are all random variables. So we are going to take expectations now. So if we take expectations on both sides, we have the expectation of njt. U is a number. U is not a random variable. It's a number that depends on t and j. So the expectation of, and now we are taking on the right-hand side the expectation of a sum. Let me remind you of a well-known property of expectations, which is linearity. So the expectation of a sum of random variables is the sum of their expectations. This is always true. Okay, always so long as you're not canceling plus and minus infinity, but always as in we don't need any independence assumptions on the random variables. It's true for any random variables with finite expectations that the expectation of the sum is the sum of the expectations. Okay, so using linearity, the expectation of njt is bounded by the expectation of the sum, which is the sum of the expectations. So the first term is u. U is not random, it's a constant. So the expectation of u is just u. And then taking the expectation inside the sum, we have the expectation of this indicator random variable. Now, indicators take values either 0 or 1. So the expectation of an indicator is just the probability that it takes the value 1. So it's the probability of the event of which it's the indicator. Okay. So the second term here is the probability of this event. Okay, I've made a change of variables. I've changed s minus 1 here to s. So s has become s plus 1. And the sum has changed from u to t minus 1 instead of u plus 1 to t. Okay, so there's a slight change of variables I've made, but other than that, I'm just writing the expectation of the indicator of an event as the probability of the event. Okay, so let me pause again to make sure that's clear. Good, so using a combinatorial lemma, we wrote the number of times arm j has been played up to time t. We bounded it in this way. And then we took expectations. And so we are now interested in the probability that these two things happen. That arm J is played at time step S plus 1. And the number of times the arm J has already been played in the previous S time steps is at least U. And okay, so how have we chosen U? We've chosen U so that this inequality here says, so let me remind you of lemma 1. You may want to go back and look at that now. Lemma 1 said that if arm J is played at time S plus 1, one of three things should happen. Either Nj should be, the number of times it's already been played should be small, or the sample mean on arm 1 should be unusually small, or the sample mean on arm J should be unusually big. So U has been chosen in such a way that one of the inequalities in the lemma is violated. Arm J has not been played too few times. It's been played at least U times, and U is big enough. Okay, so this is not a rarely played arm. So the only way you would choose to play it at time step S plus 1 is if one of the sample means behaved unusually. That's what lemma 1 is saying. Okay, so lemma 1 says that if these two things here happen, then one of these two things should be true. Either the sample mean reward on arm 1 was much lower than its true value, or the sample mean reward on arm J was much bigger than its true value. So this event here is the same as one of these two events happening. And so the probability of this is the probability of the union of this event and that event. And the probability of a union is bounded by the sum of the probabilities of these two events. That's what we are going to use next. So the expectation of Nj is bounded by U plus the sum of the probability of the union of these two events. That's what I'm writing here. The expectation of Nj is bounded by U plus the sum, the probability either arm 1 has an unusually small reward or arm J has an unusually big sample mean reward. And we have bounds on these two probabilities from lemma 3 via Hoeffding's inequality. So we get the expectation of NJT is bounded by U plus each of those was S to the minus alpha. So the sum from U to T minus 1, 2 times S to the minus alpha. And then in turn, I can bound this sum by an integral. They are approximately the same. Okay. So by doing this, you see that, okay, the sum can't be explicitly calculated, but the integral, you know how to calculate exactly. The integral of S to the minus alpha is S to the minus alpha plus 1 minus alpha plus 1. The integral at the upper limit, this is where the assumption that alpha is bigger than 1 comes in. If alpha is smaller than 1, this integral blows up. So you can, the UCB algorithm is still defined. You could carry out all the steps in the algorithm even with alpha between 0 and 1, but it gives you no guarantees about the regret. The regret could blow up. Okay, yeah, this integral here could blow up. So it doesn't tell you anything useful about the regret. But if alpha is bigger than 1, this integral is finite. And if you calculate it, you get something which is the lower limit of the integral raised to minus alpha minus 1. Now, if you looked at the definition of U, you'd see that it's at least 2. So U minus 1 is at least 1. And it's being raised to a negative power here. So it's at most this quantity is at most 1. And so you get the bound that it's u plus something. Okay, that's a bit fast, but all I want you to take away is that the second term can be bounded by a constant. So the first term is u, the second term is a constant. And so that's the bound on the number of times, the expected number of times that arm j is played. And there is one such bound for every suboptimal arm j. And now let me remind you that this u here is not a constant. It depends on j and it depends on t. The dependence on j involved a delta j term, and the dependence on t is logarithmic in t, if you go back and look at the definition. So this gives you something that is a log t over a delta j squared. So let me rewrite that. So for each suboptimal arm j, we've shown that the expected number of times it's played up to time t is bounded by, this is u. Okay, u was the smallest integer bigger than this, which adds something up to 1, and then there is this. But ignoring details, this is just some constant. You get a constant multiple of log t divided by delta j squared. This is the upper bound or the number of times arm j is played. Okay, and how much regret do you incur every time you play this arm? The regret you incur is delta j. You could have played arm 1, which would have given you reward mu1 in expectation. Instead, you played arm j, which gave you a smaller reward mu j. And so the regret is how much you lost. You lost in expectation mu1 minus mu j. This is your regret from every time you play arm j. So the total regret up to time t is just summing up the regrets from all the suboptimal arms j, delta j, the expected number of times you played arm j. And using this bound on enjt and doing some algebra, you just get this for the total regret up to time t. This was exactly the statement of the theorem. You had a logarithmic scaling in time, and you had, okay, this should be a delta j, sorry. This delta j canceled one of these things in the delta j squared. So the denominator here, there's a typo. This should be delta j as in the statement of the theorem, and that's what you get. Okay, that completes the proof of the theorem. And so we introduce the UCB algorithm and we prove that we proved an upper bound on the regret, and the main thing to take away is that the upper bound consists of a constant term which depends on how different the arms are from each other. But it also has a term that grows in t. This is maybe the more important term, or the one we are more interested in. So we have a term, so the regret grows in t, but the main takeaway message is that it grows very slowly in t. It grows only logarithmically in t. Okay, so it's a very good algorithm in that regard. We could ask for more. Okay, so we started out with a very naive heuristic, which had a regret growing linearly in t. Then we presented a clever algorithm, which improved the regret enormously from linear in t to logarithmic in t. But should we be satisfied? Could we do even better? Could we maybe get log t or log t? Is there, or even a constant not growing in t? Is that possible? And the answer turns out to be no, that there is no algorithm which can achieve regret growing slower than logarithmic in t. We won't prove this result. I'm just going to state some results related to it. So this theorem goes back to a seminal paper on multi-arm bandits by Lyon Robbins in 1985. And what they showed is the following. So they showed that, okay, there's a technicality called strongly consistent policy. The definition of that is in the lecture notes. So this is just to rule out certain silly policies. So you could decide that your lucky number is 7 and you're only going to play arm number 7 and ignore everything you observe. And then it will not even play certain arms. And so you cannot give a lower bound on the number of times that a specific suboptimal arm is played, because for every suboptimal arm except arm 7, that number is 0. But if you rule out such silly policies, then you can show that every policy must play a suboptimal arm j at least this many times. So the expected number of times that a suboptimal arm is played grows at least logarithmically in t with this constant. So this is bigger than log t over this quantity here. And here is the definition of this quantity. So this depends on the parameters, the reward parameters of arm j and the best arm mu1, which I've denoted here by mu star. Okay, so let's take a moment. So how shall I say this? So this quantity K here is called the relative entropy, or the Kullback-Leibler divergence. There's an expression for it here, and let's not look too much into the expression, but let's understand what it means. It's a measure of how similar or how different two probability distributions are from each other. So here, what are the probability distributions? They are the reward distributions on the two arms, and we've assumed them to be Bernoulli. So the best arm is Bernoulli mu1, the jth arm is Bernoulli mu j, and we are sampling these two arms and looking at the rewards. And we want to ask how distinguishable are the two arms from each other. The closer that mu j is to mu1, the more similar these distributions are to each other. And so it's harder to tell them apart from the samples. And so what it's saying is that the closer these distributions get to each other, the more likely you are to play arm j, because you cannot tell it apart from arm 1. And so but you still only play it logarithmically many times in t, but with a bigger constant, depending on 1 over k. That's the intuition. Okay, so here is a formula for the KL, we'll call it the KL divergence or the relative entropy. Those of you who are doing the information theory course will come across this quantity at some point of time. Or if you've done it already, you'll have seen this, this term. And it determines how distinguishable these two distributions are and plays a role in how often a suboptimal arm will be played. Okay, so the theorem of Lyon-Robbins tells us that no matter what algorithm you pick, it will have to play suboptimal arms at least log t times in t time steps. And so you will incur a regret which grows at least like log t. And the reason is that without playing it this many times, there isn't enough information to identify that arm 1 is better than arm j, to reliably identify that. Okay. And so if you just move this around and do some regret calculations, you see that it's bounded by Every time you play arm J, you incur a regret delta J, and you have to sum over all suboptimal arms. And this is what you get as a lower bound on the regret for any algorithm. And how does it compare with our UCB algorithm? So the UCB algorithm had only the deltas, and here we also have this extra term, the KL divergence. And to compare them, we can use something called Pinsker's inequality, which says that the KL divergence for Bernoulli distributions is bounded below by this difference P minus Q squared. And if you do the calculations, so if you assumed we had equality here, then the upper bound on regret that we calculated in theorem 1 would be 4 times the lower bound given by the Lyon-Robbins formula. Okay. So it says that in some sense, no algorithm can do more than 4 times better than the UCB algorithm. Okay, you might say 4 times better is still a lot, but I'd say it's even getting the correct scaling is quite an achievement. So the UCB algorithm is only a constant factor away from optimal, and that's not bad at all. Okay, so that's mostly all I wanted to say about this. There are variants of the UCB algorithm which are asymptotically optimal, which do meet this Lyon-Robbins bound. It's called KL-UCB. It's a bit more complicated. The analysis is much more complicated, so we won't discuss that algorithm in this course, but it's only a minor variation of the UCB algorithm. And so in terms of general principles, we have covered what is an algorithm which is already pretty close to the optimal. Okay, so that concludes our discussion of the UCB algorithm. Next week, we are going to start looking at a Bayesian algorithm for the multi-arm bandit problem. It's called Thompson sampling. And historically, it was the first algorithm proposed for the problem. And it also, it turns out in many practical experiments that it performs best. The analysis of it is much harder, and we will only give a partial analysis, but we will discuss that algorithm next time. So I'm going to stop here. Okay, so that's for next week.